Yes. Okay. Let's give it a start. It's a pleasure to have here today, Matthew Farrell. Matthew visiting for today and tomorrow. Matthew got his undergraduate degree in mathematics at Cornell University. And then did his PhD at the University of Washington in the interface between brain science and neural networks. He presenting here today. Then with some postdoctoral he has some postdoctoral positions at Harvard, and currently he has a postdoctoral position at the RIKEN Center of Brain Science in Japan, which is where it is right now. So today we'll be presenting on how and why does the brain use multiple systems to the skills. So I'll just give him an applause.
Gracias por la invitación y por esta oportunidad. Porque mi español no es muy bueno, voy a usar inglés. Esta presentación está en mi sitio web personal. So, vamos. Thank you. Yes. Great. So I'm interested in the brain as a computational machine. And I think of that as taking a set of inputs and producing a set of outputs. These desired outputs kind of capture all of the incredible things that the brain is able to do. And here I have a depiction of a rat brain, because rats are also very interesting and all sorts of animal brains are interesting. And I'm interested in what's going on inside to facilitate this transformation from input to output. Now, one way to get at this problem is to take a model which also is able to produce a similar set of mappings from inputs to outputs, or to perform the same tasks that the brain can do. And then to look inside these models and to understand better how they work, to better understand the brain. Here I have like a deep neural network, which is kind of a popular model for the brain, and also recurrent neural networks are popular models. And indeed, I like to use neural networks to model the brain because I think it captures a lot of the spirit of how the brain does computations, sort of a distributed network of many simple units that work together. And this approach is also quite influential and important, as evidenced by this Nobel Prize in Physics that was awarded for foundational discoveries and inventions that enable machine learning with artificial neural networks. Now, what this quote doesn't say is that actually when Hopfield and Hinton came up with their models, they were thinking primarily about biologically inspired neural networks as a way to solve problems. Now, these problems were not particularly difficult to solve otherwise. You can write a computer science style algorithm to do, association quite easily, just minimal Hamming distance. But the fact that you're able to do it with neural networks is quite interesting at the time, and it got a lot of excitement. And despite the fact that the problems themselves at that time weren't so revolutionary to solve, the fact that neural networks did it set the stage for neural networks to eventually be able to solve problems that were not solvable in any other way. So this is all to say that I think it's a good idea to find a brain-like way to solve even simple tasks, because this can set the foundation for solving new tasks in the future. Okay, so what is interesting about the brain? Well, here's one thing that I think is quite interesting, and it's that brain areas, a variety of different brain areas are all working together to solve tasks. Right? And there's this particularly compelling experimental example by these researchers at Harvard, where they trained a rat to tap a lever. And the rat's supposed to tap a lever with some sort of a delay period in between the two taps. And this task requires a motor cortex to learn in the first place. But after learning, you can remove the motor cortex from the animal, let the animal recover, and then test them on the task again. And you find that there's barely any change in the rat in this case. So these are just traces of the basically the pause as it's doing the tapping before and after the lesioning, the removal of the motor cortex, and it's pretty much the same. Right? And this is compelling because, well, among other things, it suggests that there's a handoff of control from motor cortex to basal ganglia. They suggest basal ganglia is where the handoff might be going, but basically from this area to somewhere else, because you take out the motor cortex and it's still able to do the task. And so if we look at the picture here, we have motor cortex and basal ganglia, which is a collection of kind of sub areas in the subcortex. These are both presumably driving motor outputs via brainstem, and they could also be talking to each other. And in fact, there's also evidence that information flow is also sensitive to the phase of the task. So in the early phases, the motor cortex is primarily sending information to basal ganglia, and striatum is one area in basal ganglia. But in the later phases, the information flow reverses. Okay. So here we have our brain. So I want to think a little bit more generally about cortex and subcortex rather than motor cortex and basal ganglia. Like it was a motor learning task, so that's what they used, but more generally we can think of this, right? And so now we can ask the question of why use a cortical system and a subcortical system. And actually, this is kind of a part of a long-standing, like let's say, theory or perspective on the brain that says that, well, it's good because one system is very powerful, the cortical system, but it's also expensive to use and resource limited, whereas the other is less powerful but has abundant resources. Okay, and so the technique you want to do is to combine these two. You want to use the cortical machinery when it really counts and the subcortical machinery otherwise. This would explain why you want to eventually, once you've mastered the task, move that information into the subcortex so it's cheaper to perform the task in the long run. And just to kind of make the point that this is not just a cortex versus subcortex division, but rather probably a whole cascade of different systems in the brain that basically weigh these trade-offs differently. At the far extreme, we have things like spinal reflexes, which are immediate, fast, cheap. Yeah. And yes, so I want to basically take this question, why use multiple systems, and ask it in a way that is, maybe a little bit denser to unpack, but more precise. I'll ask, what tasks does using multiple systems solve that using a single system does not? And, I'll make the case that a crisp framework for encoding this intuition up here is still lacking, right? So what I'm going to do is I'm going to use these three components: reward-driven learning, changing reward contingencies, and a memory constraint on the model. So take this basically view that things are constrained very seriously to kind of create a framework where this two-system model kind of emerges naturally as kind of optimal. Right. So I'll start with kind of a basic approach in the field, which says that, okay, let's treat the let's treat the cortical module as doing model-based reinforcement learning, and the subcortex as doing model-free reinforcement learning. Then we set up a simple reinforcement learning environment. So this is something that has been investigated a lot on this kind of environments with this kind of a setting. So here I have something that's called a Markov decision process, but basically it means I start at some initial state and I move through the environment, and the environment basically is non-deterministic. So I take actions, but where I wind up is according to some probability. So here I have a big probability. These will be denoted with big arrows, and the smaller probabilities are the smaller arrows. Okay. So, and then at the end of one of these paths, you get rewarded. Right, so just to run through this, I'm the animal. I start starting state as 0. I choose an action. Let's say I choose action A1. I could have also chosen A2, but here I choose A1. And I'm more likely to end up in S1, but I could end up in S2. And what happens? Okay, so I ended up in S1. That's good. So now I'm going to take action A2. So now I'm more likely to end up in G2, but actually the rat gets a little bit lucky and it ends up in G1 and it gets rewarded. Okay, so that's kind of how the environment works. This is kind of the simplest environment where you can really tease apart model-based and model-free learning. And I'll explain how that works in a little bit. Well, right now. So for the model-free learner, you associate raw action choice with reward. Whereas the model-based learner learns the transition probabilities in the environment, uses these to calculate the most likely path to the reward. So you can estimate the transition probability. So I'm assuming that the animal doesn't know this ahead of time, so it has to learn it through experience. So you can just take the number of times that you go from, let's say, S0 to S1, taking action A1, and divide it by the total number of times you took action A1 in S0. So this will give you an estimate of the probability that you'll wind up in S1 if you start in S0 and take action A1. Right. And so let's kind of take a look at the difference between model-free and model-based. So here, remember that the rat took action A2 and then wound up getting rewarded. So for the model-free learning paradigm, this would strengthen the action of A2. So the rat would be more likely to take action A2 when it's in state S1. However, if the rat has pretty good estimate of the probabilities in the environment, then it can use that to understand that actually, even though I took A2 to get and got rewarded, what I actually want to do is take action A1, because A1 is more likely to get me to G1 and get the reward. So basically, the model-based learner would strengthen action A1 in this situation, and the model-free learner would strengthen action A2. So that's kind of a difference in how they behave. But actually, you can use both model-free and model-based together, and this is something that these works also consider. So this looks something like this. So here on the left, I have the model-free learner, and this will use something like a temporal difference learning rule. SARSA is kind of the name of this. And on the right, I have a model-based learner, and this will be using something like dynamic programming, using the estimated probability distribution, probability transitions to do that calculation, right? And ultimately, you can derive a Q function by taking a combination of these two. And for instance, this is one way that it's done. You just take a weighting of the two Q functions. And okay, just to give an overview, these Q functions in reinforcement learning, they are basically an estimate for what reward you are expecting to get if you take action A in state S. So these are like surrogates for, these are basically your expected reward that you're learning. So you take a convex combination of these two. That's one way to form Q, your ultimate Q. And you can do things like fit this W to human behavioral data. And you find that even though in this setting, it's always better to use more information in the environment. So it's always better to use model-based learning. Despite that, you still find that W is greater than 1, which means that, for humans, which means that humans are not using a purely model-based learning. They're actually using quite a bit of model-free component in their decision-making. And this is explained, like I said, with saying, well, model-free is cheaper, so that's why humans don't use purely model-based approaches because it's too expensive. But the thing is that this combination, and the combinations that have been considered before, I would say don't fully or properly take into consideration this resource constraint perspective. Because here you're still computing the full model-based Q function, and you're just combining it ad hoc. But really what you'd like to do, if you want to take that perspective seriously, is you want to form this Q function by actually constraining, putting some real constraints on it, right? So our proposal is to place a memory constraint on the model-based learner. So I'll show you how that works, right? So for instance, let's say that I am only going to allow myself to track 4 transitions in the environment. I'm only going to be estimating at any given moment 4 of these probability transitions. So for instance, it might look like this, right? So I don't have any information about the probability distributions of these transitions. I only, let's say, choose to track this for this. This is pretty natural because if you imagine that you are doing the same task as a human, the rats, it's kind of a lot of mental energy to, consciously track all of these probability distributions. but you're probably going to eventually learn some of these probability distributions at least. So, it's kind of a natural model, I think, for actual cognitive effort. Okay, and sorry, so just to like make this more compact to draw, I will combine these together. And this means, the red arrows basically have both model-free and model-based, but they're also being tracked by the model-based learner, whereas the blue arrows are only model-free, using model-free information. Okay. And so the equations to basically form the Q values from a combination of these two sources is, so the first one is the model-based component. This is a dynamic programming style update. So you can see I'm using the estimated transition probabilities here. I'm multiplying it by, my kind of what I observe to be the reward, or what I understand to be the reward in the environment, and then this value function, which is itself computed from the Q function. But importantly, I only compute this if this edge, so each of these here is an edge, is being tracked. Just say it's colored red here. So if the edge is colored red, then I use this equation. If it's not colored red, then I use just the model-free Q value. So this is the way it's almost, instead of just taking a convex combination of the two Q values, I kind of do a parcellation over the environment. Right, and okay, so this was our proposal, and this is, here in the preprint that we have. And yeah, so this basically opens up this idea of memory allocation strategies, because now I only have a set number of edges that I'm allowed to color red. So the question becomes, which of these edges should I color red? And which of the edges do people or animals actually color red, right? So these, and for instance, here's two possibilities. So I could choose to color these red because, maybe the reward comes here. So I choose to put all my resources into exploiting reward. Or I could choose to color these edges red because I want to be able to get to any arbitrary end state most effectively. So if I understand the transition dynamics of near the root of the tree, this gives me maximal, basically, power to be able to get to an arbitrary end state. So these are two different strategies. Okay, now for a static task where I just have the reward in like one location and it never changes, the strategy is a bit obvious. There's not really any reason to do anything other than just color all the edges red, which lead to the reward. And you want to kind of prioritize those that are closest to the edge first, but then they should all be leading to reward. So, basically from this perspective, it seems that subcortex and cortex could be physically co-located because they're both basically computing reward in similar ways. They're both just looking for the reward and processing all their information. So these edges use the reward information, or the model-based learner uses the reward information to decide which edges to track, and also uses the reward to update the Q values. So, you could have neurons that are just all together here. The red ones are, coding for transition probabilities and reward, and the blue ones are, encoding for the model-free. I don't know, it seems like they could potentially be together. Now, there are other reasons why these two brain, types of neurons might be separated, like physically separated into cortex and subcortex. But I kind of wanted to add more to that. So another reason why it's good to actually have a separated motor cortex and a separated subcortex. And this can kind of answer the question of why do we have two different brain regions that are physically separated working on the same problem. Okay, so in order to get at this, let's consider a more naturalistic setting, which is one of changing reward contingency. So what this means is that the reward can change from this location to this location. And now the optimal strategy becomes a lot less obvious because this strategy is actually, even during phase one, where the reward is here, it's learning information that's useful for phase two when the reward gets over here. Whereas this one is only learning information that's useful for phase one. And then in phase two, it needs to kind of adapt to that. So, I've been talking about these different strategies a lot. So let's go ahead and give them a name. So this strategy I'll call max reward, where I'm always trying to track the edges that lead me to reward to maximally support reward exploitation. And this one I'll call max reach because it's maximizing my ability to reach an arbitrary goal state, right? So during phase one, when the reward is here, this strategy would seek to color these edges red. And then when the reward moves, so this can be dynamic, right? So all that matters is that at any given time, I have no more than 4 edges colored red because that is my memory constraint. But I can change it. I can move from here to down here. So now I'm tracking these edges because the reward has moved. Whereas this one kind of gets a head start, but then this component will never be tracked. So maybe in the end, it won't be as good. So let's see what it actually looks like in a little bit. All right. So first off, the exact specifics for how right. So the exact specifics for how these edges are tracked through the learning process is a bit more detailed than what I described here, because there's issues of like how do you break ties. But you can see the paper for the exact algorithms with this. But for the intuition I give, like exploiting reward versus being able to maximally reach your arbitrary end state, that's pretty good for understanding the essence of these two strategies. Okay, now let's look at the results of what this looks like. So here I have this line, which is the model-based learner. So this is, has full knowledge of the environment. And then I also have a line which corresponds to purely model-free. So these kind of act as loose upper and lower bounds of the learning process. And then in the middle here, I have my two candidate strategies, max reward and max reach. So during phase one, we see that max reward does better, which is not too surprising because I'm using all of my resources to learn how to exploit the reward, right? Whereas the max reach doesn't do quite as well. But we see that when I transition, so here at episode 200, the reward switches from here to down here. Then you see that the max reach for a period of time actually does better than the max reward. So in the initial phases of learning, the fact that I already have been learning this information during phase one gives me a boost. Yeah, I'm able to learn faster. But in the long run, max reward is able to catch up because it's also learning the spectrum model structure, which eventually allows it to do better. But then they all kind of converge together again. Right? So you can see that there's kind of a complex trade-off. Now, if non-stationarity is the dominant factor and early reward here is important, then it's possible that max reach can be a better strategy. So there are some situations where max reach would be a better strategy. And this strategy is interesting because it means that the structure of the world is learned somewhat independently of reward. This means that the edges that I choose to track are not influenced by reward. And this has some interesting implications. This is kind of a dominant strategy in cortex. It might help elucidate why cortex is physically separated from subcortex because both areas are using reward information differently. So the cortex needs to be very careful about basically which neurons receive reward relevant information because many of the neurons which are responsible for learning a model of the world should be ignoring the reward. And we know that in areas like the basal ganglia, like striatum, these areas are quite heavily basically get many projections from dopamine modulated reward signals. Right? So it's kind of a flood of dopamine modulated reward. So it kind of makes sense that you'd want the motor cortex to be some distance away from that heavy reward signal, and so that the those dopamine neurons can kind of be more precisely wired there. Right. So here we had this is kind of the big blob theory of motor cortex basal ganglia. Why isn't it just one big blob? Okay, well maybe it's because reward, is strongly projecting to the subcortical regions, but it's projecting in a more delicate and light way to the cortical regions. Right. So this is one possible explanation. Yeah.
What's the objective of learning? Like an automata model system, or is it just an algorithm?
So it's a policy. So it's a map from state action. Yeah. So basically the Q values are used to write a policy through like epsilon greedy or something like that.
Okay, so you have a bunch of rules, right?
A bunch of what?
Rules.
Yes.
Okay.
It is, and it's tabular, so that's the bunch of rules kind of perspective on reinforcement learning.
Okay.
At every state, your policy tells you how, like, how often should I choose action A1 and how often should I choose action A2? And that's ultimately what you're trying to learn. Yeah. Yeah.
That's for model-based part,
That's for both. Both learn a policy.
but the free one is not probabilistic.
It is.
What's the difference?
So you learn a Q function with the equations that I have, and then so it can be deterministic. You can just do an argmax with a Q function. Just take the action which maximizes the Q function. But the problem with that is you oftentimes get locked into suboptimal solutions. So oftentimes there's some amount of exploration. The simplest approach, and the one I take, is called epsilon greedy. It means do the thing that maximizes the Q function like 80% of the time, and then 20% of the time do something random. So that's the randomness component of the policy. Yeah. And that's the same for model-based and model-free. It's really how do you compute the Q values where the difference comes in. Yeah, with the equations that I showed before. Okay. I guess. Yeah.
So you're considering the tabular set, right?
Yes. This has all been tabular. Okay. So, let's see how I'm doing on time. Start 1:40. We have till, when do we go till?
1:30, 1:35-ish.
2:30.
2:30.
So that should be good. Okay, so I can go into this. Okay, so I basically described a theory.
So, sorry?
Yeah.
Is there any relation to the size of the number of states or anything in how fast does max reward take over?
Yeah. So that is all, yeah, a function of like how deep the tree is and how many edges. So we plot a bunch of different results here. What's a simple takeaway? So I think that, well, for one thing, if you're model-based, if the red arrows cover the entire environment, then these two things do exactly the same thing. So there's no, so basically the more limited, the more extreme this difference is. Yeah, and that limitation is emphasized both by making the environment larger and keeping the number of edges fixed, or by decreasing the number of edges you're allowed to track, right? So it's like a fraction.
Like that, and then
Yeah. And the exact relationship is something I'm still kind of trying to work out. I don't think it's so similar, like it's just the fraction, right? I think it's a little more complicated than that. But yeah, that would be kind of the intuition. Yeah.
So if you have an animal in a real environment, how do we imagine that the animal gets the information of the shape of this graph?
Yeah, so the typical way of doing it is just by showing pictures, I think. So there's a picture that you see that's associated with S1, S0, like a random picture.
So every state has a marker.
Yeah. Uniquely identified, so each state is unique. And then the animal has like two buttons that it can push, A1 or A2. It pushes a button and then it sees a new picture. That's the usual way.
So in this way, you try to constrain the inner representation of the animal to fit with the graph. But this in theory, the animal might consider that some markers belong to a same class, so that their model is not exactly the red subgraph, but it's some other graph related to that, right?
Yeah, you could take another parameterization of the space. For instance, maybe the animal roughly learns the probabilities, part of the probabilities of all the left ones and then all the rights. There's other ways of taking combinations of it. So I am assuming here that it breaks down along these actual probability distributions. But yeah, in general, you want to consider parameterized models, which could do different combinations, linear combinations of these features. Yeah. Yeah.
Because in RL, people, I mean, I'm thinking about these papers like Dreamer, the Dreamer papers. So they basically, they try to train an RL model to play Minecraft, say. And so they try to build a word model,
Yeah.
which is, they call it like this is model-based RL.
Yeah.
And then this word model, they don't impose anything and somehow it has to discover a graph.
Yeah.
But I mean, so in a sense, I was wondering how easy to translate between this, I mean, I agree that this is easier to kind of control what is going on.
Right. Yeah, so typically there, your constraints are implicit. However big the neural network is, that represents that model-based component. And like how much resources you put towards that versus other things is, an art, mostly. Try different things. So I guess this is an attempt to make this more systematic, to build a theory of that. And yeah, you're right that to get all the way there, we need to consider parametric models. So neural networks of different sizes and see how that scales rather than just.
So basically your budget of red arrows would correspond to what is my budget of my neural network.
Yeah. How many parameters or whatever. Yep. And then, so you could build a theory in that space as well. It'd be more difficult, but yeah.
I was wondering how sort of the proposal that you have differs from the medicamati work where you basically plan and to do some habit behavior. It seems very similar here that you can sort of frame this in this view, right?
Sorry, what was the name that you said?
Medicamati, bigger guy and big 2016.
Yeah.
Where they basically sort of provide these views that when you have like a deeper sort of trees, we develop these you plan until a horizon, and then you sort of behave in a model-free way.
Yes, that is another way of combining the model-based and the model-free learners together, right? So you have a limited number of steps that you're able to like plan ahead. So I think that is basically taking this more in the direction of planning. Here I'm focused on probability transition probability estimation because it's sort of simpler and it builds on, I guess, work that ties more closely to like the brain stuff that I'm familiar with at least. But yes, another way to extend this would be to consider planning. So I guess in that case, it would be building a theory for how many steps you should take in planning, or just generally how many resources you should give to that, and then at what point, and how many steps do animals take. But maybe I should review that to see exactly what they do. Sure. Okay. Any more questions or? Okay. All right. So, okay. Maybe we have two modules. Because of this. So, what I'd like to be able to do is to now ask the question of what strategy, like what arrows are animals actually painting red, right? And what's kind of nice about this is that this is a very well-established kind of behavioral experimental paradigm, right? There's all those papers that I've presented before that use this. So you can really kind of investigate this. So basically, it works like this. You have an animal, and it is taking actions in the environment. And those actions, actually, since I had a lot of questions, should I extend the time?
We have more time, don't worry.
Okay, because
We'll extend, don't worry about that.
skip this. Okay. So, right. So the animal is just going about taking actions. So what you do is you take that history, all those trajectories, all the states and actions that the animal experiences, and you just feed that into whatever learner you want, whatever model. So the model could be the max reach algorithm. It could be max reward. And then at a certain point, you ask, okay, so the animal is here. It's at this state in the environment. Now, what does the model predict the animal is going to do next? What action does the model predict the animal is going to do? Max reach might say, well, the animal is probably going to take this action. Max reward might say, no, the animal is going to take this action. So what you do is you basically give a 1 if the algorithm predicts the action that is actually in the data that the animal actually took. Now, at this point, I don't have an animal and I don't have data. So instead, I artificially generate the data with strategy. So I have these two strategies. One of them I use to just generate data, and the other I basically compare with and see how consistent it is with that data, right? And on the diagonals here, I just have a comparison of the strategy with itself. Right? So this is like a baseline, basically. And on the off diagonals, these are the cross comparisons. And here on the right, I just subtract the baseline basically from the cross comparison. What we can see is that the biggest difference between what the strategy predicts will happen and what actually happens in the data occurs right at this mark where the transition is from phase 1 to phase 2. So when the reward changes location, and it's happens specifically, so this action stage, right? So for a depth 2 treat, there are 2 actions that the animal takes every episode. And so every time it goes through the environment. And so it's specifically action 1 when the reward changes where you get this big change in, or this big detection of inconsistency. And that makes sense because these arrows here, these red painted arrows, are the biggest difference between max reach and max reward. Whereas max reach has been learning these transition probabilities when max reward hasn't. So right when the reward switches to down here, max reach will quickly do the right thing and max reward will not. So there will be a biggest difference here between the 2 strategies. So you could use this to estimate what animals are actually doing by basically taking a bunch of different strategies, doing this type of comparison analysis or consistency analysis. And you know, not only do you get an overall consistency, but you can see when and where the algorithm is consistent with the animal. So basically the game would be to find something that's closest to 0 here. And that would be the thing that the animal is presumably doing. Those are the arrows that the animal is painting red. Okay, so to conclude, I propose an extension of existing paradigms for combining model-based and model-free learning, which this is a pretty influential line of work, and which also considers these resource constraints directly. And these resource constraints are also very influential perspectives. So kind of took 2 influential things and actually put them together. And these constraints provide a normative picture for where model-based learning should occur in an environment. So which arrows should you paint red? And this tentatively suggests that cortex and subcortex might use reward differently, which means that they might need to be physically separated. And we also showed in the paper how data can be analyzed to measure consistency, so like actual animal data with different proposed like model strategies. And not just how much, but when. So to go further, I would actually like to collect and analyze data. So this is something that I'm planning now to see which memory allotment strategies animals actually use. And another direction to go in would be to consider more realistic tasks, doing actual difficult decisions that machine learning people would be interested in. I'm also interested in other cortical functions, kind of related to that. Here I only consider transition probability estimation, but there are things like planning, imitation learning, all sorts of different functions which are cortical in nature and be interested to add to the model. And all of these things should be limited, right, with resource constraints. I also considered, I'd also like to consider parametric models instead of just tabular, and communication between cortex and subcortex is something that can be considered more as well as a wider normative framework. So here I'm interested in, building, combining like offline data demonstrations. These are cortical type of things. Then here's the task, multitask learning. So I only considered a simple form of multitask learning here. And then also a lot of different energy constraints than just memory. So like energy, compute, space, and time. So these are all things that would be interesting. And this is kind of like a grand overview of the framework that I want to push towards. And there's also something called transient spine dynamics, where motor cortex it creates new connections when you're learning a new task, and then it erases them. So that's kind of like having a hot cache, and it's an interesting way of basically saving memory. But I should continue. And so I want to look a little bit more at this component, which is communication between cortex and subcortex. Okay, So in this model, we assume that subcortex only receives information from cortex via action selection. Right, so this is the equation, and in pictures, it basically looks like this. So the model-based module, this part here, it can use information from the model-free module because the V function can be a function of Q and F, and also which edges you choose to track. It's sometimes useful to use the model-free information, but the model-free module here does not use information from the model-based module. Only via the actions that you choose, which are fed back into it. Right? But it's possible that cortex guides subcortex more directly. So this would be like putting a double-sided arrow. Now, so this would look like, right? Just to give an illustration. So I choose two actions, and the model-based learner, learns faster than the model-free learner. So it will quickly be able to realize that the correct thing to do in this situation is to take action A2 and then action A2. Right, so the first action would be A2, the second action would be A2. And so it'd be useful if we could actually provide this information to subcortex so that it can actually learn faster. All right, so let's look at kind of a general sequence of actions, not just two, but general depth tree or general process or whatever. And so another component of the subcortical learning is that of automaticity, that eventually the sequence should be carried out autonomously from a starting point. So this kind of transforms you from using a policy into just using a simple map. And this introduces the idea of a sequence memory. So basically, if the subcortex has access to these actions, it can learn a map from one action to the next. So it can just generate these actions and spit them out. And this is something that is observed in biology, and for instance, the birdsong learning circuit, where you have like layers of neurons which are in a feed-forward cascade, and it goes from like one to the other. So this layer of neurons will activate, and then this layer of neurons will activate. So you see this discrete activation, and this corresponds to the point in the song that the animal is singing. So we see this kind of encoding in the brain. And then you can turn these actions into actual motor outputs by learning associative maps. Okay, so let's look at how this is kind of done traditionally. Right. So this is like a collection of classical models, which works like this. So we have like two patterns here. These are encodings of the two actions. And to build a transition from one action to the next, we construct a weight matrix like this. This is the outer product of the two vectors. And this matrix encodes a transition from one pattern to the next. Right? Because if I multiply by pattern one, you take the inner product of pattern one with itself, you get a big number that cancels out, the one over n cancels it out, and you're left with a vector that is basically proportional to the second pattern. You can then define a dynamics on a neural network. So this would be like a firing rate model. So these R's represent the firing rates of the neurons to get an actual neural network which implements this transition from pattern one to pattern two. And to get a full sequence out of it, you can just add these different components, right? So here's from pattern one to pattern two to pattern three, etc. So this gives you a full sequence. Now, to basically measure the state of the network, you can define these overlaps, which tells you what state is the network in. So you get one for each of these patterns. So each of these colors here corresponds with a different pattern, right? So 1, 2, 3, blue, blah, blah, blah. And you see that, so for instance, for pattern two, you start at 0, so the overlap is small. The network then aligns itself to basically match with pattern two, and then it decays again as the network starts to align with pattern three. So this shows you the sequential behavior of the network. And to get an even simpler view of this, you can take the peak times of these patterns, these T-mus. So these tell you basically what the temporal dynamics of the sequence is that the network is generating, right? And to learn this, you can assume basically that something like motor cortex is setting the network state to these different pattern values, kind of in chunks of time. And then you can apply Hebbian learning. So these are learning rules that you see in the brain, just this convolution with a kernel. And if you use this kernel, which is just an offset delta function, then you recover this weight structure, basically. However, in biology, you actually see a variety of these different weighting functions. It's not just a delta function offset. So we were interested in this, and we wanted to generalize the traditional models to use general W, right? So here is like the classical model where we just have these components 1 to 2, 2 to 3. But if you have a general W instead of this delta function, then you get also components that look like a transition from pattern 1 to 3, 2 to 4. You get these components where it's an auto-associative term. And then you can even get transitions backwards in the sequence. And then the W will determine the actual coefficient weighting values for each of these components. So, and this goes on. So ultimately you get a weight structure that generally looks like this. So this is kind of a new structure of these sequence models that we introduced here. But even though that you have all this rich structure, you still get sequences that look, like the classical sequences. And so what we want to do now is describe the actual behavior of this general model. Right, so again, I have these dynamics, and we're interested in these overlaps, right? So, and this gives us this picture here. So if you take the size of the network to infinity, you can basically compute that the equations for the overlaps look like this. And this is basically, this g of t is some mysterious nonlinear function. But using the theory of large couplets matrices, you can actually show that g of t is going towards a particular value. It has a limiting value, right? So here I'm plotting this g of t function, and you can see that it is asymptoting to these values. And this dotted line is given by 1 over the sum of these coefficient values. Now, the exception is when this 1 over the sum is too big, it goes beyond a limit. So this limit g, big G, is determined by the phi function. And actually, this corresponds to the pattern decaying away exponentially fast. So this is like a failure mode. But if the sequences are being recalled successfully, then you see this g of t function asymptotes to this constant value and quite quickly. So this means that we can turn this nonlinear system of equations into an approximate linear one so I define these normalized coefficient values, and then this is what the equations turn into, replacing this g of t with this limiting value. So now we have a system of linear equations, right? Okay, so now we have this linear system of equations. So now we want to derive the dynamics from it. So since it's linear, if we give it periodic boundary conditions, so this gives us a circulant coefficient matrix, which means that we know what the eigenvectors and eigenvalues are. And so writing those down, you get this approximate solution. So usually what you do in this kind of situation is do something like a saddle point approximation. But actually it works better, turns out, to just do kind of the simpler thing and just expand out these cosine and sine functions out to two terms. This gives you quadratic forms here in the exponent. And that's exactly the form that allows you to apply the Hubbard-Stratinovich identity and turn this complex integral into just a simple function. Right? So you get this value here. And then this x and this y, are written in terms of the coefficients. And these coefficients are determined by that the integral of the kernel. Okay, and so those can be. Now, to get the location of these peak times, you just solve q dot equals 0. And so you find that these are where the peak times occur. Right? So this allows you to say what is the temporal dynamics of this sequence model in terms of the coefficients, which is determined by the Hebbian learning kernel, and as well as the Tudor signal timing. Okay, so from this you get the sequence recall speed, and you also get stability, which I won't go into here, but you can also derive that, which says that the sequences decay exponentially fast. Okay, and this is just a quick result. This is just to show that actually the theory works. Right? So I have basically the simulations, the linear approximation I described before, and then the final approximation that we have after doing the expansion and Hubbard-Stratinovich. So you can see that match as well for over a range of these different coefficient values that we use. Okay. So to summarize, I considered a long-standing class of sequence models used in computational neuroscience. And this is also a model of cortical tutoring of subcortex. I asked, how do these models behave under more realistic general learning rules that we see in the brain? And I expanded this class significantly and mathematically described the essential attributes such as the recall speed and the recall stability. This is important because, generally, we can make predictions that say, Well, your learning rule should make it so that your sequence recall speed is faithful, which means that whatever the tutor signal timing was, the recall should be the same speed. Or you could say, well, I want to model fast replay events. So actually the recall speed should be much faster than the tutor signal. So these are the things, and then you can predict what the learning rules should be that give rise to that. And this sheds light on the process by which the brain might learn and store sequential programs, such as motor outputs. Now, in the future, I'd like to actually do, let's say, a better job of incorporating this perspective into the actual reinforcement learning framework, and to kind of give a more normative account in this framework. Okay, so kind of the obligatory job talk works overview slide here before I close. So, I'm interested in, well, a lot of these papers look at normative frameworks to better understand brain function, which is what I'm interested in, and most use neural networks, maybe all except for this most recent one, which in the future I would like to use neural networks by considering parameterized models. And this is, my model of cortex and subcortex joint learning, and this is a model for cortex tutoring subcortex directly. And these two things basically come from very different worlds. Like I connected them with a bridge, but the bridge is still a little bit light. And actually it'd be good to bring these two worlds together more completely, right? They very different, like they're both classical, like subfields, but they're on the top function. So it'd be good to have that. Okay, and finally, I will just acknowledge my collaborators. So in this work, these bold are people who I worked with on the papers, and then also people in the group who helped me by giving me feedback and things of that nature. And this was done jointly at RIKEN, and the sequence model was at Harvard. So thank you.
Any questions?
Thank you very much for the talk. I'm curious about translating the first part of the talk to say something that can be perhaps leveraged to devise better neural network architecture. So I'm wondering if you see some kind of way to use this kind of model-free and model-based learning to maybe improve the neural network or devise ways to train that better use this to make it more robust. I mean,
yeah,
is this connection feasible? How do you see it?
I think so. In fact, the pruning is basically what is seen, which is really interesting. Motor cortex actually generates all these new connections when you're learning a new task, and then prunes them. So there's a very clear, setting for that. And I would really like to get at that level of the neural network and to start to ask, what is the best neural network? Of course, once you get there, you have a lot of choices, what neural network architecture to use. So it's really important, I think, to establish the normative framework, the task, because now you can compare and to really constrain, really what you want to do is you almost want to have like a minimal description length constraint, like almost an information theory type of thing on the model, because then you could sort of maybe compare neural networks, tabular, have them all constrained in the way that's balanced, right? Because it becomes a little difficult what counts as a parameter, what counts as a memory slot. But yeah, it would be great to build the theory there, and then you could say, okay, under this constraint, which neural network is the best?
The third part of the process was mentioned that you focus on tabular setting.
Yes.
I'm not sure if that is good. If you are doing same purpose updates or passing updates.
The updates that I'm actually doing are this is a kind of a hard to get. They start at the reward and then they flow backwards, and I do it in I use the updated Q value immediately in the update to the next one. So what this means is that the reward information immediately propagates to the root of the tree, because I think that this is a smart thing to do. So I think the brain probably does something like that. So that means it's not synchronous, but there's this particular order to how things are updated, which there's some justification for
the model base that proposed.
Yeah.
What was the sampling intensity of how does it work? More or less you have to sample and then optimize, so how do you manage that? You take an episode for sampling and then you optimize, so.
Yeah, so everything is kind of mushed together, which is a simpler thing. Yeah, in general, you would want to consider, well, and sampling can also be simulated trajectories, but everything here, there's no simulated trajectories, it's just basically model has a policy. It uses that policy to drive its behavior. It collects the data from that trajectory, and it uses it to update the Q values, which then update the policy. So it's a very simple account of this. So the sampling is purely experiencing the environment via the policy, which combines the model free and the model based.
And do you have estimates of something complexity overall? How does it relate? Just lots of speed of variables.
This is something I'd really like to be able to do to actually predict at least the overall rate of those lines and how they relate to the how many arrows you paint red and which arrows you paint red, right? I've played around with it a little bit, but so far the assumptions I have to make to get an answer are a little bit too strong for me to feel like they're that useful. So still working on that. So no, I don't know a theory for the sampling complexity. Yeah. It's actually somewhat complicated.
Well, the question.
Yeah.
Of the decision process of where do you focus on, which links to five. Is it connected to this? I don't remember exactly. I think it's UCD type of social learning, where where you focus on estimating the actions that really are processed. And that you keep track of some confidence intervals.
Right, yeah, the confidence. And so actually maybe the most influential paper in this area chooses between the model based and the model free based on their estimates of their own confidence. So I have not looked at that yet, but you know what, I guess all of these things can be used to define a strategy. I've defined max reward and max reach in my own way. If you want to add in all of these different flavors, you could do that. It defines a strategy, and then you can compare with the brain. So I'm hoping that this theory at least sets a foundation. Sorts of things could be done just by taking into consideration the insight, which is the memory constraint, or whatever constraint you're interested in. So yeah, all of those things would be interesting to look at, and would have to be motivated a little bit by considering both the normative, how many resources, because if you're estimating it's interesting because if you're estimating confidence intervals, that takes parameters to do. So you can still kind of play this game and compare in a normative way, which is better to do. Yeah, and then also compare with like what we know about the brain to see which is most likely thing that's happening. So yeah, all those things would be interesting. Extensions, different algorithms, different model-based algorithms, different model-free algorithms.
And from a more practical point of view, is there data that can experimental data that can use to give your models or compare? Or
I have a student working on that now. He has not found something that I can just plug and play yet. So it looks like we may have to run our own experiments, but it's still too early in the process to be totally sure about that.
the biologists or neurobiologists, they don't have often.
I kind of think so because it's such a simple task, but what was the reason why we couldn't necessarily use it? So one thing that you need, so oftentimes it's just with this very shallow tree. So we could give it a shot, but oftentimes it's like this. And it's very possible that the animal or a person can memorize all these transition probabilities. So we may want to make the tree deeper to really make sure we're saturating the limits. But I guess, if this is enough, if this already overtaxes people's ability, and actually, I guess the fact that people don't do a purely model-based strategy in the setting, maybe we could just use that data actually. The same data that was used by Nathaniel Dodd in these sorts of tests, yeah. It'd be worth a shot at least, because the data's there to see, yeah. That's a good point.
Thank you. I had a question on the last part of the sequence model. Wondering, so maybe I missed it, but so basically your model was to replicate sort of tempo sequences.
Yeah.
And so I have two questions that I sort of. They're sort of notoriously unstable, sort of to generate sequences, right? And so I was wondering how robust is the model, specifically in terms of sort of the spacing between these two signals.
Yeah.
And then the other question, I guess it's also a bit related to the fact that as humans we can learn a specific tempo and we can sort of dynamically modulate that tempo without any further learning, right? So I was wondering if the model, because I played with this model, right? So
Yeah.
I was wondering if you guys tried to do that as well.
Oh, yeah. Yeah. We have not tried to do that. We focused on just this, like the underlying scaffold part of the problem, but then modulating with like other words, other theory that's been done. I think that you could probably just put it right on top of this, maybe. And then you could get that modulation, that dynamic modulation. But it's kind of the question of what should be that like default speed, or the base speed. And then for the first question, right, which was, oh, the instability, right? So yeah, I kind of, for simplicity's sake, I kind of played fast and loose with that. The reality is that you would not have just a map from action, 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 action. You'd use some amount of proprioception. And the question is how much, and how, basically. So there should be a flow from using more information to drive your policy and using less and less and using as little as you can, basically. So it should be like a minimization of that. So you'd use like the minimal proprioceptive information you can use to perform the thing. Like when you're playing piano, as you get really good at it, I mean, you're more or less just doing the motor outputs. But yes, you are adjusting somewhat based on the field. So yeah, that to really have a faithful model, you need some amount of inputs from proprioception.
And the heavy learning rules, they were like Xcal type rules or ECM learning rules.
What was the first thing you said?
Xcal basically have this delta, sort of, it's not just X, Y, right? It's like sort of X minus something.
Yeah.
X, Y.
Yeah, so we had like a delta function offset. And you need the basically, if you don't have the offset, you just get like a Hopfield network.
Yeah.
The offset gives you the sequence. Basically what we did is we said, well, what if you have like a double-sided exponential kernel that's like lopsided, right? Because this is continuous in time. And then, well, especially if it has non-finite support, then obviously you're gonna get like components which combine all the different terms of the sequence together. So yeah, that's what we did.
Okay, the final round of applause.